Alright, welcome back to another video. We are going to talk in this video mostly about a two-sample t-interval. Alright, so when you're comparing this to a one-sample t-interval, you kind of want to think about how you're going to get this form. So recall for a one-sample t-interval, we talked about x bar plus or minus t star times the standard deviation of the statistic divided by the square root of n. Now this should be similar to what we did in chapter 8 when we talked about how to do a one sample t-interval. All right, with the addition of the second sample with the two sample, we know that this is not going to be a single x bar anymore. So similar to what we discussed yesterday, we're going to have the difference of two means instead of the difference of two proportions. So instead of having just a single x bar, we now have two, and we're going to take the difference, and we're going to be interested in that difference. T star is just going to drop down here, and it's going to become t star. Now that might be a little bit more different to calculate, but we're going to go through it. But the standard deviation of the statistic is going to be similar to the sampling distribution, the difference of two means. So we are going to take the square root, we are going to take s sub x squared divided by n, and then add that to s sub x squared divided by n. Now we do need to notate that these, like the first ones being with a 1, and the second one's being with a 2. All right, so I know there's kind of like a lot of notation going on there, but it should make sense that this is going to be the form that you're going to get when we do this. So very, very similar there. All right, I'm going to erase this stuff over here so you don't get too confused. So there's your form there, so make sure you go ahead and copy that down in your notes. All right, and we're just going to go through some of the conditions. Whoops, some of the condition checks there. Oh, I did it again. Right. Okay, conditions for inference is going to be very similar to the conditions for inference from the last unit. Again, I'm going to go ahead and emphasize the two independent random samples there, or randomly assigned groups. All right, but making sure that we use the words two and independent when describing our conditions for inference for a two-sample procedure are very, very important. So I'm going to highlight those and make some notations on the screen. This normality check is very similar to what you watched in the previous videos for two-sample sampling distributions. You can have one of three things going on. So the sampling distribution is going to be approximately normal if the population distribution is normal. So if the population is normal, so will the sample distribution. If not, you can then refer to the sample sizes. If they are both greater than or equal to 30, remember this is when you can make a central limit theorem statement. And we should be pretty good at making those central limit theorem statements now. And then if either of them are below, excuse me, that 30 threshold, we need to graph both data sets. And this is when we're going to talk about making like parallel box plots. That'll probably be the easiest, I believe. If sigma 1 and sigma 2 are both unknown, we're going to use S1 and S2 to estimate. Very similar to what we did for the last unit. Okay, so if sigma is unknown, we're going to use S of x to estimate, which means we are going to use these T procedures that we've been discussing. Great. Now the degrees of freedom in T star are going to be slightly different, but we're just going to rely on our calculator to obtain those. I wouldn't really worry about how the calculator computes it. It's going to be a little tricky, but just kind of take your calculator's word on it. All right. Our example is going to be about two fire stations within a certain town, and they're responding to calls in the northern half of the town, and the other fire station responds to the calls in the southern half. So you have one in the north and one in the south. One of the town council members believes that the two fire stations have different mean response times. So they are going to tell you that the mean response time is measured by the difference between the time an emergency call comes in to the fire station and the time that the first fire truck arrives at the scene of the fire. So data were collected on this information to investigate whether the council member's belief is correct. So let's go back and see what the council member believes. They believe, one of the town council members believes that they have different mean response times. All right, so that's the claim that they're talking about there, different mean response times. So we have random samples of 50 calls selected from the Northern Fire Station, where we have a mean response time of 4.3 minutes with standard deviation of 3.7. Another random sample of 50 calls from the Southern Fire Station with mean response time 5.3 and standard deviation 3.2. So our goal today is going to be constructing and interpreting a 95% confidence interval. So construct and interpret this means that we are going to do a panic procedure for the difference in the mean response times between the two fire stations. And then we have a follow-up question that we will tackle afterwards, talking about, does our interval in part A support the council member belief that two fire stations had different mean response times? And we're going to talk about how to go through that. All right, so we're going to do a panic. So we should start off with our parameter. So we want to estimate the true difference in the means, where we have the mean sub n minus the mean sub s with 95% confidence there. So we're going to estimate the true difference within those means, and we're going to do north minus south. Remember, you are able to do south minus north if you so choose. You just need to make sure you notate that here. So if you do choose to subtract the opposite way, that's perfectly fine. Just make sure you note that. You do need to make sure that you state both parameters. Parameters here being the true mean response time of both the Northern Fire Station and the Southern Fire Station respectively. So make sure that you copy those down. Please feel free to pause if you need to in order to jot this down, but we're going to continue. So our assumptions, we do have three. First assumption there being independent random samples of 50 calls from both the Northern and the Southern Fire Stations. All right, again, with the word independent, that is why it's bolded and underlined. Remember, the whole premise of this Chapter 10 unit is going to be to talk about independent random samples. We have more than one sample, so we need to make sure that we note that when we do our inference procedure. All right, normality. Since our sample sizes for both stations is high, in this case, both are greater than or equal to 30, we can assume normality for the sampling distributions of the response times for each station due to the central limit theorem. So we may assume that we are approximately normal. You can also do this in notation. So if you chose not to write this all in words, of the response times for each station, you can do x bar n minus x bar s, if you so choose. It's the same idea. And then here we should note, that both sigma n and sigma s are unknown, so we must use Sn and S sub s to estimate. All right, very, very similar to how we did one sample t intervals, but now we're just doing it with a second sample. So we do have a second sample size we need to discuss, and we do have a second standard deviation we must look at and make a comment on. This allows us, again, to use these t procedures at this point. And the sample, or the name of our interval, is going to be a two-sample t interval. All right, and we're interested in estimating the mean difference in these response times here. Moving on there, we are going to be using in the calculator option 0. So today's test is going to be a two-sample t interval, which is done in the calculator by going to stat tests and going to 0 and choosing that one. I highly encourage that we organize some information first, and on the next slide we will talk about it, but organizing some information first. So go ahead and pause the video and make sure that you jot all this information down so that you're able to plug it into the confidence interval formula that we're going to discuss now on the next slide. So go ahead and pause now if you need to. All right, moving on for the interval there. So go ahead and jot down the formula. Feel free to pause as you need in order to jot down some stuff. Next part we're going to do here is we are going to plug this all in. Your calculator will talk something about pooling. We do not pool within AP statistics. If you're interested in the pooling idea, We will discuss that in class, or you may look in your textbook. They have a nice little section on why you pool versus why you don't. But going and unplugging all of the information in there into its respective spots. So here it looks like the difference there of 4.3 minus 5.3 is going to give you -1 in front, and then times the, or plus or minus t star times that standard deviation of the statistic there. So you can see that we have 3.7 squared and 3.2 squared, all underneath the square root, divided both by 50 and then summed together, kind of like you see there. All right, so here is going to be your interval, and you're actually going to need this in order to go back and find t star. So doing a two-sample t-interval is a little bit weird because you can't actually find t star until you put it all in the calculator. So at this point, just go ahead and find the interval using your 0 option there. And it's going to give you a degrees of freedom. So we're going to use the degrees of freedom that you obtained here. So you should have 96 for that. So from your calculator, what you're going to do now is you're going to go back and plug this in, the degrees of freedom, to find your t star. So you should get 1.98, but let's go back over how you got 1.98. Remember, to do this, we need to use inverse t within the calculator. I wasn't supposed to do that, but that's a giant inverse t. So we have the area, so remember that's where your area goes, followed by the degrees of freedom, I believe. I'm going to check my calculator just to make sure. I think it's just area and degrees of freedom. It is. Degrees of freedom, we're just going to plug in 96. Remember, you do not need to subtract 1 because it's already degrees of freedom. And then area should be that 0.975. Now remember that 0.975 comes from taking 95% confidence. So remember, we're doing a confidence level of 95%. Remember that we always do 1 minus 0.95 divided by 2, and then we add that to 0.95 to give you the area there. I think it's also shown to you by doing the normal curve, where you have the 95% there, where you have 0.025 on both sides there. And then remember that that t star is going to be that upper t statistic, and we're going to look at everything below there. So that's why we get the 0.975, because we had the 0.025 plus 0.95, blah, blah, blah. You guys probably already know that. If you didn't, well, you didn't pay attention in Chapter 8, but there you go. So 1.98, once you plug that in the calculator, you do get the interval of -2.37 to 0.37, and you are now able to conclude. So we are going to state here that we have, we are 95% confident that the interval from -2.37 to 0.37, and then we're going to use units here, which is going to be minutes, captures the true mean difference in the response times between the northern and the southern fire stations. So we are 95% confident that the difference in their response times is between -2.37 minutes to 0.37 minutes there. All right, and you do not need to copy down the result, but when we're thinking about answering, I guess, that part B, we need to realize that there's a possibility of no difference. And remember that we talked about this with one proportion, or not one proportion, but two proportion z intervals. When there is no difference, that means that the mean of n minus the mean of s should be equal to 0, which means that these true response times would be the same. So no difference would mean that the response would be the same, which means that there would be no difference, so it would be 0 in terms of the difference between them. So let's use that to answer the question in part B. So we are simply just going to say that since the interval contains 0, which it does, notice that 0 is right in the middle there, so 0 is inside. All right, we are going to reject the council member's belief. It's not supported. So there is a potential there that the mean difference there is 0. So if there is a potential there that it is 0, well, I mean, you have pretty good evidence that it's not supported. Remember, his belief, if you remember at the beginning of the problem, was that there was difference. And here we have evidence that there's not, because 0 is within that interval. Remember, if 0 is within the interval, this is similar to failing to reject HO for a two-sided test. So I'm going to jot that down because I think you guys should really start connecting the ideas between a two-sample test and how to do that with a two-sided test in the confidence interval. So it's like failing to reject HO when you have a two-sided test. So zeros inside. And I think we talked about this when we did the other one. So same idea, just with means. All right, I think that wraps up this video. You do have an assignment that goes along with this, so make sure that you work on that. See you next time.